Hello, everybody. Welcome to Unit 7 test part 2 review. These are all the free response questions. So I try to make them very similar to what's on the real test. So yeah, let's get right into it. The teacher has 30 students in their class. Every day, the teacher selects one of the students at random to be the classroom helper. The probability the student chosen does not have any brothers or sisters is 0.2. What is meant by probability in this setting? It means that, well, oh, come on now. Don't do this to me already. It means that 20%, right? Because that's what 0.2 is. 20% of students do not have a brother or sister. There we go. Now, part B, some days the teacher selects 5 students at random with replacement. For one of these days, the first 2 students selected do not have any brothers or sisters. What is the probability the next student randomly selected does not have any brothers or sisters? Well, because it's still with replacement, meaning that once I pick a student, I put them back in the pool and pick again. It's always 20%. So everybody's always accounted for the next attempt because, like I said, you pull one and they go back, and then you pull again and they go back. So you're using the same set of people over and over again. If it's 20% the first time, it's going to be 20% every time. So it's still 0.2. For one of the groups of 5 students, the teacher selected a total of 3 of them. Selected a total of 3 of them did not have any brothers or sisters. The teacher was surprised at this result. Describe how to conduct 100 trials of a simulation to determine if the teacher should be surprised that at least 3 of the 5 students selected did not have any brothers or sisters. So yeah, 5 students were picked and 3 of them did not have brothers or sisters. We're looking to see if that's a surprise. It says, describe how to conduct 100 trials of a simulation. So my probability is 20%. So I have to find a way to simulate 20%. So I can pick like maybe a number generator from 1 to 10. And I can have 1 and 2 represent not having a sibling. And obviously 3 through 10 being has a sibling, because that's 20% and 80%. I could also use, and it's kind of a coincidence in this case, I could also use the numbers 1 through 5. 1 would come up 20% of the time, and then 2, 3, 4, 5 would come up 80% of the time. So it's not really the numbers that matter, it's the probability you're using. So you could use, I'll just list a couple options here. You could use 1 through 5, with 1 being no sibling, and then 2 through 5 being yes sibling. You could use 1 through 10. 1 and 2 could represent no sibling, and 3 through 10 could represent yes. You could use 1 through 100 if you wanted to, where 1 through 20 represent no sibling, and 21 through 100 represent yes, a sibling. So any of these would count because it's all 20% to 80%. I'm going to use the most simplest one, which is the 1 through 5. So I'll say, let me kind of zoom in a little bit. Choose or generate numbers between 1 and 5. Let 1 represent no sibling. Let 2 through 5 represent having a sibling. And then because we have to pick 5 students, it would be generate 5 numbers. Generate 5 numbers and count how many ones appear. So another way to say this, if you used like the 1 through 10, is you could say generate numbers between 1 and 10. Let 1 and 2 represent no sibling. Let 3 to 10 represent having a sibling. Generate 5 numbers and count how many ones and twos appear, right? Or if you were to use the 1 through 100 numbers, you could say generate numbers between 1 and 100. Let 1 through 20 represent no sibling. Let 21 through 100 represent having a sibling. Generate 5 numbers and count how many 1 through 20 appear. See, it's all the same thing. But yeah, as long as the numbers represent a 20% chance, then you're good. All right, number 2. The probability that a randomly selected person in the United States is left-handed is about 0.14. Among the 28 students in Mr. Hedon's AP Statistics class, 8 are left-handed. Describe how you would use a random number generator to simulate the proportion of left-handers in a class of 28 students if they were chosen randomly by a population that is 14% left-handed. So it's kind of like what we said before. Now it's 14%, right? So I'm going to use, I'm just going to simply go with 1 to 100 and using 1 through 14 and then 15 through 100. So, simply say generate 28 numbers between 1 and 100. And let 1 through 14 represent left-handed. Let 15 through 100 represent, I guess, right-handed. And then count how many numbers between 1 and 14 show up. The graph on the right shows the number of left-handed students in 100 simulated classes of 28 students. Assuming that students are selected randomly from a population in which 14% of individuals are left-handed. Explain what the dot at 0 represents. So this means there is a simulation. In this case, there are 3 simulations, right? There were 3 trials, 3 simulations where 28 numbers were generated and none were between 1 and 14. Right? They would have generated 28 numbers, and this says that there were 0 numbers that were between 1 and 14, which represent left-handed people. So 0 were left-handed out of that set of 28. And that happened 3 times. Use the results of the simulation to estimate the probability that there would be 8 or more left-handed students in a class of 28 students if the proportion of left-handed in the United States was 0.14. So 8 or more. So 8 or more, you can see that's 4 out of 100, right? So 4 out of 100 or 4%, right? Or I guess you can put it as decimal form, 0.04. What do these results suggest about the proportion of lefties in Mr. Miller's class? I guess that he has kind of a rare event of having a lot of left-handers. So he has more left-handed students than, I'll say 96% of the population. Right? Because he's in the top 4%. 4% chance to be 8 or more, which means that I would assume that 96% of classes are less than that, right? It's 96% of classes have 7 or less. So yeah, he has more left-handed students than 96% of the population. All right, a teacher at a local high school surveyed the senior students. Two of the variables recorded for the 200 students or whether the student has any siblings or whether the student typically drives to school. The following table summarizes the responses. Choose a senior at random. Let D be the event the student drives to school and S be the event they have at least one sibling. What's the probability that a randomly chosen senior from this high school drives to school? So, okay, so drives to school. So we have 130 that drive to school out of 200. So 130 out of 200, which is about 65%, so 0.65. All right, easy peasy. That's good. Make a Venn diagram to display the sample space for this process. Okay, so Venn diagram. It's not going to be the biggest, but it'll work. Let me see if I can do this. I'm going to zoom in a little bit more so I can kind of make better use of my space here. So we have driving and we have sibling. Now we have driving and sibling have 80 people who are both, as you can see in the chart there, 80. Driving without a sibling, that's 40. So that's going to be 40 here. Oh, wait, no, hold on. Driving without a sibling is 50. My apologies. 50. Because that's this number here. Driving, yes. Sibling, no. Sibling, yes, but driving, no. Sibling, yes. Driving, no. That's this 40 right here. And then 30% don't drive and don't have a sibling. Not 30%, sorry. 30 of them. So that's a Venn diagram to represent that chart, basically. Write the event a senior does not drive to school and has at least one sibling symbolically and find it. So probability, a senior does not drive to school. So driving complement and has at least one sibling and S. All right. So that's simple. Driving to school, or I'm sorry, does not drive to school and has a sibling. So does not drive to school. No. Has sibling. Yes, that's 40. Right? 40 out of, I guess, the total amount of people, which is 200. Right? 40 people do not drive to school and have a sibling out of 200 people in total. So this comes out to be 20% or 0.2, if you want to put it like that. All right. Number 4, a survey of 4,826 randomly selected college students were asked, what do you think of the chances you will have much more? What do you think are the chances you will have much more than a middle class income at age 30? The two-way table summarizes the responses. Choose a survey respondent at random. Define events G as a good chance, S expect to earn Bachelor of Science, N as almost no chance. Find G given S. So, all right, so G means a good chance given they expect to earn a Bachelor's of Science. So, this would be probability of G and S over probability of S. So if you focus on this, a good chance is this right here. So of that, we're talking about, I'm sorry, of people, S is expected, oh, sorry, expect to earn a bachelor's degree. So of bachelor degree, so of this group, how many of them suggested a good chance? So 663 people think to have a good chance and expect to have a bachelor's of science out of the total of people who have a bachelor of science, which is 2367. So it's 663 out of the 2367, which proportionally comes up to this out 663 divided by 2367 as 0.28. So essentially 28% of people who expect to have a BS degree, Bachelor of Science degree, by the way, think they have a good chance of making more than middle class. All right. Kind of runs into B a little bit. Given that the chosen student didn't say almost no chance, what's the probability that this person expects to earn a BS, a Bachelor of Science? Write your answer as a probability statement using correct symbols and notation. So, given they didn't say almost no chance, so given it's any of these other people, given they didn't say almost no chance, so given out of that many people, what's the probability this person expects to earn a Bachelor of Science? So Bachelor of Science is this many out of that total. So we have 426 plus 696 plus 663 plus 486 out of 712 plus 1416 plus 1421 plus 1083. So we put all that together real quick. That's going to take a minute. 426 plus 696 plus. Just going to type this in. 46, then divide by 712 plus 1416 plus 1421 plus 1083. Assuming I didn't type anything in wrong, it's 0.49. All right. Yeah, as far as using the correct symbols go, it's probability. Not really. Almost no chance. So didn't say almost no chance would be n complement. Oh, it's given that. So given they didn't say that, given n complement. Probability that they expected to earn a BS. So S. So this is be the notation, given again what it said earlier about the notation up here. So not almost no chance. And then a BS degree. So they expect to earn a BS degree given that they didn't say almost no chance. All right, and then a final question. Or not final, there's 5 and 6. So next final question. A manager of a restaurant was wondering a manager of a restaurant was wondering, I guess, wondering if, I guess it's supposed to say if, that's a weird typo, was wondering if there was a relationship between the types of meals purchased, steak or chicken, and the time of day, lunchtime and dinner time. Let event C as a customer purchase, let event C as a customer purchase chicken meal, and let D represent, I think it just mistyped some of these, represent that it was dinner time. The manager randomly selected 150 checks from all of the checks from 1 week of sales. The two-way table below summarizes the results. What is the probability that a randomly chosen person from this sample orders chicken for their meal? Be sure to include a symbolic representation of this question. Randomly chosen person sample from the sample orders chicken. So just probability they order chicken. Well, we had 80 people order chicken out of 150, right? So 80 out of 150. So 80 out of 150 comes out to what? 0.53. All right, what does P probability of C given D represent in context? So it means probability someone ordered chicken given they ate dinner. So probability someone ordered chicken given they ate dinner. So what probability, basically, what's the probability of somebody ordering chicken at dinner? Essentially is that. Find the value of that. So C given D. So it would be C and D at the top over D at the bottom. So C and D, chicken and dinner is 35 out of dinner in general. Dinner in general was 85. 35 out of 85. So 85 people eat dinner and 35 of them ate chicken. So 35 out of 85 was 0.41. And then are they independent? Well, as you can see, we already had probability of chicken and we had probability of chicken given dinner, and these would have to be equal to each other. But you can see we had 0.53 and 0.41. These are not equal, so they are not independent. All right, and then finally, number 6. A game is played by rolling a die. If the die is a 1 or a 2, a player draws a marble out of bag A. If the player rolls any other number, the player draws a marble out of bag B. Bag A has 8 marbles in it, 2 of which are black, 6 of which are red. Bag B has 12 marbles in it, 8 of which are black, 4 of which are red. After drawing a marble, the marble is put back in the bag. If a player draws a black marble, what is the probability the player rolled a 1 or a 2? All right. So, game is played by rolling a die. If the die is a 1 or a 2, the player draws a marble out of the bag. Okay. If the player rolls any other number, player pulls a marble out of bag B. Okay, so we're going to end up pulling either out of bag A or bag B. Now, bag A would be if we rolled a 1 or a 2, which a 1 or a 2 has a 1/3 chance of happening, right? 2 out of 6. 2 out of 6 is 1/3, which means that there's a 2/3 chance, or 4 out of 6, that we would choose from bag B. Does this make sense? We're going to either pull from bag A or bag B. If I roll a 1 or a 2, I pull from bag A. That's a 1 out of 3 chance of happening. If I roll a 3, 4, 5, or 6, I pull from bag B, which is a 2/3 chance of happening. All right. Bag A has 8 marbles in it, 2 of which are black and 6 of which are red. Bag B has 12 marbles in it. Okay, so if I go to bag A and I pull a marble, let's see, it has 8 marbles in it, 2 of which are black, 6 of which are red. So we can do a black marble or a red marble. So black marble, there's 2 out of 8, so that's 0.25. And then 6 out of 8 are red, so that's 0.75. I could probably just put the fraction there, I guess. Right? I'll just put 1/4. Actually, forget about it. I'm going to make these match the right values from there. So 2 out of 6, 4 out of 6. I know it's not simplified, but it'll be okay. This was 2 out of 8, and this would be 6 out of 8, just to make it a little bit easier to understand if you're reading this at home. All right. And then bag B has 12 marbles in it, 8 of which are black. So black, 8 out of 12. And then red would be 4 out of 12. All right, there you go. After drawing a marble, the marble is put back in the bag. If a player draws a black marble, what is the probability the player rolled a 1 or a 2? All right, so we want to find the probabilities here at the ends. And for the sake of convenience, I'll put it in decimal form. So we have 2 6 times 2 8. So that's essentially 4 out of 48. which comes out to 0.083. Then I have 2 6 times 6 eighths, which is 12 out of 48, which is 0.25. Then I have 4 6 times 8 twelfths, which will be 32 out of, what's 6 times 12? 32 out of 72. So 32 out of 72, which is 0.44. And then finally, 4 6 times 4 twelfths is going to be 16 out of 72, which is 0.22. And if I added these all up, it should get me pretty close to 1. I know I rounded a bit, but if you did 0.083 plus 0.25 plus 0.44 plus 0.22, it's 0.993. So we're off just a little bit because of rounding, but it's okay. All right. So the problem here says if a player draws a black marble, so given that they draw a black marble, the player draws a black marble. So probability someone given they drew a black marble. What's the probability the player rolled a 1 or a 2? Which means they picked bag A, right? 1 or a 2 means they picked bag A. All right, so they picked the black marble from bag A. So we'd have probability of A and black marble over the probability of a black marble. Now these numbers, A and the black marble, was the 0.083, right? A and the black marble, 0.083. Out of the total of black marble, which would add these two together, 0.83 plus 0.44. So we added those together, 0.083 plus 0.44, you get 0.523. And I'm going to put on the side here how we got that. So this was again 0.083 plus 0.44. Right. Which comes out to hold on, mistype that real quick. This is 0.083 divided by 0.523. About 16% equals 0.16. It's rounded a little bit. There you go. All right. Could be a little bit tricky for sure, but hopefully you can kind of see how I set this all up. Just remember A represent, rolling a 1 or a 2. Anything else, a 3, 4, 5, or 6 was bag B. And then once I knew which bag I was going to go into, then I picked a marble. And if I was in bag A, 2 out of 8 would be black, 6 out of 8 would be red. If I went to bag B, 8 out of 12 are going to be black, 4 out of 12 are going to be red. And that just helped me to get all the probabilities. Once I had it set up, once I had these numbers in red, it becomes a lot easier. So it said again, if a player draws a black marble, so we already need to just focus on the black marble, right? This amount of marble. What's the probability they rolled a 1 or a 2, which basically just translates to came from bag A. So it's this many out of the total of this many. That makes sense. That's how I got it. All right. I'll leave it there. It's a long one, but it's not the most convenient, not the easiest, but you guys can do it. If you have questions, just let me know. And I'll see you in class, and good luck on your test. Bye for now.